Bienvenidos al ciclo de seminarios del Departamento de Química, trimestre 24P. Agradecemos a los que nos acompañan de manera presencial en el R206 y a los que nos acompañan de manera virtual a través del enlace en YouTube. Le cedo la palabra al profesor Garza para la presentación del expositor del día de hoy. Adelante,
Sí,
profesor Garza.
muchas gracias a todos. Well, it's a pleasure for this university to welcome Professor Paul Ayers. He doesn't need any introduction about his work. Everybody knows that he's a giant in quantum chemistry. Paul visited us 20 years ago or 22 years ago, maybe. He was
21.
a child.
21.
Yes, he was a child. But since then, he was clear that he was making a lot of contribution for this field in chemistry. So for that reason, we are very happy that he stay here again in our university. One of the projects that he reflects who he is will be the focus in this seminar. Our friend Raimundo Hernandez Esparza was involved in this project, and for that reason, Paul wanted to present this seminar at Raimundo's alma mater. Thank you very much for this gift, Paul.
Okay,
Thanks.
thank you, Jorge. So while we get started here, I just want to say it's wonderful to be back at WAM. Jorge is right. I was here, I think it was 21 years ago. It was my first research visit as a professor, was to WAM. At that point, many of the people who now have some distinction in that had none, right? But yes, but we're all more experienced and hopefully I can give you a better talk now than I would have then. Okay, no, thank you. Okay, I'm going to have to figure out. Should I come over here to change my slides or just tell you? Okay, well, I'm going to tell you something about what, as Jorge already said, I'm going to tell you something about what I was doing together with Raimundo, but also a lot of other people. And so I'm dedicating this talk to Raimundo Hernandez Esparza. He was really made a major impact in the life of my group. And we'll talk some about the types of things he was doing as we get deeper into this presentation. I'm going to first start about what he was not doing, right? And so I think sometimes about my career as having different pieces. And the first 10 years of my career, I would say, was what I called slash and burn science, right? What do I mean by slash and burn science? Well, the same thing you mean by slash and burn agriculture. Basically, you have something you want to do and you don't care what you have to do in order to do it, right? And there's basically I could list my 7 deadly sins of here I've listed 4 basically. And basically all of these I did early in my career, right? People who know what I was doing early in my career know that I don't do that anymore. And that was because I was way too overconfident in what I was doing. Jose Luis and myself talked about the fact that I spent a good chunk of the first 10 years of my career working on kinetic energy density functionals. And that is a very hard problem. No, back. I just told you I did try to do things fast and not sustainable. The next slide will show you that. I was a little bit too worried about following the herd, right? Which I don't recommend. And then this is, I always call this is the biggest problem for science. I didn't have a problem with this one, which is why I'm here. So you can basically screw all the rest of this up as long as you work hard, it'll be okay, right? The next slide. So what I mean is it was unsustainable. It says something about my record system that I can still find my old files from this period. This is one of many directories associated with population analysis. And this was my version control system, right? We have, you know, I was doing Renier. Obviously, at some point it was messy, and so I had clean. This is clean 2. Who knows what happened to clean 1? There's Renier Plus, which does something that the original one didn't do. There's one, it was slow. I made it fast, right? There's main 2 and main 3. Then there's Renier 2, Renier Lambda. This is probably a Lagrange multiplier in there somewhere. Salus, so obviously Renier at some point got, then there's fast Renier 2. There's another Renier clean. There's a Renier just labeled October. Who knows? And then something both, which probably is Renier and Salus put together, but I have no idea, right? The main point is, I was working like this. People in my group was working like this. And what that meant is the second that someone graduated, then poof, it's all gone, right? There's no way for anyone except me, probably not even me, to make heads or tails of this anymore, right? So this is what I mean by slash and burn science. Like I had certain objectives, and the simplest thing to do was take the old code and make it fast and name it fast old code, right? So this is, you know, an example of how not to do things. Okay. Now I'm going to warn you, you're going to have to, so I'm just giving you instructions here. As I go through these, you're going to have to click on this button. Okay, you see, okay? So now, but go back for one. Okay, so I'm going to give you a brief history of Horton, which is roughly when this sort of thing stopped, okay? When I started to do something other than slash and burn science. It was 2007, so not my first research visit, but one of my early ones. I visited Ghent. I had been working on pair density functional theory, which no one does anymore for good reasons. That was something that I pridefully believed was going to be useful and was not. And I met Dimitri Van Neck, who literally wrote the book on many body theory. And we started talking about reduced density matrices. And while I was there, I met one of his graduate students. And I'm hoping, so I will tell you the story of Tone, and I just want all the students here to realize I'm going to be here. And one of the things, Tone was a graduate student. He was working on a project, and he didn't really understand how he was getting the numbers he was getting. And at that point, I was much less busy than I am now. And I just sat down with him. And I tried to understand what he was doing. And I said, I think you're doing this. Why don't you see if you can delete this part of your code and you'll still get the same answer? It turns out my contribution to this paper was that I took a gigantic program and replaced it by a single call to a singular value decomposition. So he had basically invented his singular value decomposition from scratch, which was, I mean, give him credit, very, very clever. But just a very convoluted way of doing singular value decomposition. So, but that was, you know, and I'm here, so for the students and the faculty too, sure, why not? Like, this is the sort of thing I enjoy doing. We just sat down, we digged into it, and we figured it out. But the thing that was amazing for me, you just saw my programming style, was that I would have an idea to test, and he could very quickly test it, because he was using this weird new language called Python, right? And so, you know, I would say, why don't you try this? He wouldn't just test it and say, oh, it works, it doesn't work. He would show me plots, right? And I was used to Fortran, where to make a plot was, ugh. I mean, so this sort of got me started thinking about it. And so we at some point decided we had some project together. The project actually, this will be interesting to Jose Luis and some of the others, was on constrained DFT. That was what we were trying to do. We realized that we couldn't do what we wanted to do with normal codes. It was too painful. We needed to write our own code from scratch. And that became Horton 1, which was helpful open source research tool for in-electron systems, right? Now we say in-body systems because it will do bosons and fermions and all sorts of stuff, but in-electron systems. And this is, both of us looking very young and really deciding for what we want to do, we have to build an ecosystem. We need to build an environment to do the type of research we want to do, right? So, some of you, the ones in the front rows, can read The Simpsons here, just having to write on the board over and over again, I will not cut corners, right? And we didn't cut corners the way I had been cutting corners, right? We did some very good things, but there were some bad things too. Like we used version control, like real version control, not like giant directories. We had automatic testing, we had documentation. We're probably one of the first, quantum chemistry codes to have decent documentation at this point. And it was a Python code with everything that was slow had been dumped into C++. Unfortunately, some things that hadn't been slow, but we thought might be slow, but we hadn't really tested, we just dumped it into C++. It was better safe than sorry. And so that was our sort of the first thing. And then one of my graduate students at that time, who some of you know, Arnaz Haydar-Zada, she split off the post-processing. At this point, Horton was this giant monolithic code, just like Gaussian or anything. And at some point, it's like, you know what? All the stuff you do after a calculation, we'd be able to run population analysis or compute the Fukui function or something like this, not just after we did Horton. We'd like to be able to do it after we did Gaussian or after we did Orca or after we did Psi4. Why don't we take it away and disentangle it from Horton so that you can do ChemTools on top of anything? And so ChemTools, the post-processing thing, got split off and way back in 2014. It's 10 years. It doesn't feel like 10 years, but it's been 10 years now. And it's now maintained separately. It's a separate little project, right? But the first realization that this giant monolithic code was a bad idea, right? Then this, in 2014, we decided that there were problems with Horton 1 and we need to come up with Horton 2, right? This is the diagram for Horton 2. This is a piece of paper that we wrote down the way Horton 2 was going to work. This was actually written down in Chile, which we'll see as a theme for like killing and then resurrecting Horton. It happens in Chile. So this was in Chile. Several of us are visiting Carlos Cardenas, and we did it. There's a bunch of names here that are most of them still involved in Horton. The one thing that now I look at this and I'm just horrified is anytime you write a spec for a program and it has this many arrows and arrows crossing arrows and things like this, it's problems, right? This is not the way to build software. But we didn't know any better at that time. It was, as I said, a monolithic traditional program. It was designed to be something like a Gaussian, but something that we controlled and might be a little bit easier for us to modify. So I've tried to say good things and bad things here, right? So the good thing is we have what they call continuous integration deployment. So every time someone made an update to the code, it would automatically get tested. It would automatically get pushed onto the internet for other people to use it. We noticed that people don't like getting feedback on their science. Like none of us like getting referee reports. No one likes us to criticize their writing. People don't like people to criticize their code either. And so we ended up writing a bunch of scripts that would take people's code and give them feedback on it. Because if you curse at the computer, it doesn't really care. But if you curse at the person who was trying to help you, they really get upset, right? And so we had scripts for quality insurance to make sure things were documented, to make sure things were tested. Basically, we reviewed things by hand, but only after it had already gone through a long list of sort of automatic checks. In fact, right now we do the same thing. We have all of these checks. Then there's an artificial intelligence check, and then there's a human check, right? That's the modern iteration of this. There was the same problem that we use C++ whenever we thought it might be useful. We just use it just for the sake of using it. There was something called the matrix class. It's what they call linear algebra factory. And the idea is you outsource all of your linear algebra operations into this little factory that for your code, so that and that in principle was a wonderful idea, and in practice was terrible, because if you know anything about quantum chemistry, there's one thing that every bit of your code uses, which is linear algebra, which meant that when people didn't want to think about where something belonged, they put it in this linear algebra closet. And then this closet became very cluttered, it became very disorganized, became impossible to deal with. And then this sort of was the end of this sort of monolithic Horton 2. And so this is what I would call a closed-ish ecosystem, right? It's an ecosystem, right? It isn't slash and burn, but it's closed. And for those of us who are old, like the people who were here when I was here the last time, you may remember biosphere, right? This is this idea. They built this giant thing in the desert. And the idea was you would have a self-contained living environment, and you could learn how the world and how, you can make sustainable agriculture and everything. Everything that we learned from this, we could have learned if we had just read the Wikipedia article about biosphere ahead of time. And since the text is small, I'll read it to you because this is just almost comical the way things go wrong. It says, Biosphere 2 was only used twice for its original intended purposes as a closed system experiments. Both attempts ran into problems, including low amounts of food and oxygen, die-offs of many animals and plants included in the experiment, group dynamic tensions among the resident crew, outside politics, and a power struggle over management and direction of the project. So everyone who's ever been part of a big project is just like, yes, like, and so we decided that this was not the way to go, right? It was an improvement over the last one, but it was still a giant headache. And also you have to realize that there was only one person. So in software companies, they talk about benevolent dictator for life, right? There was only one person who could be benevolent dictator for life, and that was me, and I didn't want to be benevolent dictator for life, right? So this is where Raimundo actually entered the picture. He is the first and only person who's ever been hired exclusively to work on this software package, right? So this actually is a picture. There was a Canadian software package, Canadian software conference in Montreal. And we went there. We found a Horton, right? Which is why we have a picture with this elephant. And we had a very good time. In fact, I'll tell you, for those of you who know Raimundo, he comes from a family of bakers, right? His family has a bakery, right? And so going to Montreal and going in one afternoon, this was on our way to all of the leading bake shops in Montreal to try them and compare them. That was our afternoon excursion when we did this. I have no idea how many bagels were in our bellies at this point, this picture, but nonetheless, that was our excursion was a guided tour of Montreal bagels. Right? Okay. So really, when Raimundo was still with me, though Raimundo sort of mid-pandemic started working remotely instead of still working at McMaster, there was no point. We spent 2 years working from home, right? We decided that we needed to do something different. We talked about, then that's Horton 3. This was right before the pandemic. This was in February in Chile. You will recognize, so Fernaz is the one who split off Chem Tools. And there is Tone, less hair and more gray than before. There's me, less hair and more gray than before. And Esteban Voringer, who has sort of joined the team at this point, right? So he's sort of, now there's sort of maybe 6 faculty that are major involved in this project, but these were the 4 main ones at this point. And so we decided to basically restart from scratch. And I'll try to explain to you why and what we ended up doing. And we'll see some of the things that Raimundo was doing as we were in this process. So why? In scientific software, they have something called the bus factor. The bus factor is the number of developers that have to be hit by a bus before your project is unsustainable, right? And at this point, our bus factor was, let's say, 1.5, right? It was like Tone and Fernaz, and if, you know, ChemTools would have been gone without Fernaz, and Horton would have been gone without Tone. And so basically, we're sort of at 1.5, right? We could have sustained something, but not everything. And we realized that this closed system wasn't working because you had to have all of this politics going on. And most scientists don't like politics. I know there are scientists who like politics, right? But I'm not one of them, right? And so we wanted to distribute the development work. We wanted to make it so that not one person was responsible for everything. We wanted to make it more, they're talking about fair in software and fair in data. We wanted to make it more accessible. We wanted to make it easier to use Horton with other packages. We kept getting people writing us and said, oh, we'd really like this feature of Horton for our package. But because Horton was a giant package, it was impossible to say, oh, just take this feature, right? We couldn't do that. We wanted to be easier for us to reuse Horton for different purposes, right? So I can give you an example from the new version. We started writing a geometry optimizer. It became a general optimizer. We use it for orbital optimization, for geometry optimization, for optimizing generic functions that show up other places in research, right? You write good code and it can be used in lots of different contexts, some you never saw before, right? So at that point, we got Horton 3, and the main idea was we divide it into pieces. And individual pieces have a lead 1 or 2 developers, so that in general, all of these pieces, they're usually 2 people who sort of know it top to bottom, which means the bus factor for every piece is 2, and the bus factor for the whole project is much more 2, right? I'll just quickly go through, we'll see most of it. We have something for input and output. So this is designed to make it so we interface well with other programs. So we can read output files from almost anything, including some solid state codes. And we can then convert it into something that would be useful for another program. In fact, you can just convert file formats in this way, but also we can do post-processing and things like this. We have a functional Gaussian basis set tool, which lets you do all sorts of fun things with Gaussian basis sets, right? We have a mean field Hamiltonian. This is the piece that has turned out to be the hardest to get working because we have it's easy to make it work easily. It's hard to make it work the way we want it to work. But it has something to do with Hartree-Fock, Kohn-Sham, things like this. We have a post-Hartree-Fock module. We call it PyCI. This is the second post-Hartree-Fock module for this program. The first one was wonderful, but too slow, and so we've rewritten it. We have a geometry optimizer. I told you a little bit about geometry optimization. And then we have something for doing all sorts of numerical integrals or plotting things on grids, any differentiating things on grids, anything where you need to do numerical integration, differentiation, interpolation, things like this. And so basically, the idea is all of these are independent modules. If you decide that you would really like to use our integration methods, you can use our integration methods, and you don't have to decide to also use our Kohn-Sham code, right? You can use one piece of this. You can say, our geometry optimization methods are better than Gaussian. You can just run them with Gaussian instead of geometry optimization and Gaussian. You don't have to try to use our Hartree-Fock Kohn-Sham code, right? So the idea is that they're each separate. They're maintained by separate people. And Horton at this stage is only the glue code. Horton is just often a Jupyter notebook that uses these things to do something, right? And ChemTools, we did the same thing too, because ChemTools was starting to get big also. And so we divided ChemTools into individual pieces, and you no longer need to have every piece of ChemTools. Now, this project is a little bit behind. We've been prioritizing Horton right now. But for instance, we have a lot of stuff on topological analysis and quantum theory of atoms and molecules, and we have I think, a very good code for that. And you can take that piece of the code, and you don't need to choose all the rest of ChemTools. We have partitioning methods, and I'll show you a little bit of the partitioning code. We have, I think, very good stuff for conceptual density functional theory. We have something we're coding right now, which is for conceptual density matrix functional theory. So doing density matrices instead of density functionals. We can do all sorts of other things like molecular orbital things, non-covalent interactions, electron localization functions, things like this. So each of these sort of becomes its own little piece based on what types of information you need and what type of goals you're trying to get out of, right? So again, and also you'll notice, and I noticed I said it here, the elephant logo is gone, right? Because now ChemTools is really separate from Horton. So ChemTools, in fact, now usually gets used with PySCF or Gaussian. So, right? The last little thing here is that when we did Horton, we didn't totally kill off the old Horton. We realized that some people, there are many people, but some people still use it. And so we migrated it to Python 3. So it still works. I don't recommend it. In fact, I highly unrecommend it. But if you really want to run it, you can run it, right? We still use it, but we don't maintain it. We just try to make sure it doesn't die. And in a year or so, we'll just let it die, right? It's too much work to keep it alive for no one. And so what we did is we decided that we would set this up as a software consortium, right? Now we have, I think, last time I checked, there are 90 people who've done some sort of contribution to this group. And it's basically a community that we do sustainable software. It's now not just quantum chemistry. We have some people doing things in data science and machine learning and device physics and other types of things that you wouldn't recognize as chemistry. But they sort of joined this thing. We have sort of a setup for setting up programs. We're committed. Everything will be 100% free and open source. It's all going to be on GitHub. And we tried really to make sure things are customizable, that they're user-friendly, that they're documented, that everything's tested. And basically, we think of this as our collaboration platform, right? It's a platform that we collaborate with lots of other people on lots of different things. And that's one reason that we've ended up now with a couple more people who sort of joined the team, because we aren't just chemists anymore. And I'm not sure if it's going to work, but I'll try to maybe show you. But if you may find it interesting to go to QC-EDU, because we set up also sort of an educational piece of this, which has things on software design, but also, for instance, my quantum chemistry course now is entirely online. So anyone who wants to take, quantum chemistry from McMaster, or, you can basically see exactly what McMaster people get in quantum chemistry, down to having assignments and getting automatic grading and automatic feedback on your assignments and things like this. Okay. I think a space bar will move you to the next slide, but maybe not. So if not, yeah, one more, there we go. Okay, so I want to tell you a little bit about, sort of give you demo. This isn't going to look exactly like it would look like on my computer, but I think it will still look okay. This is going to be adventurous. But basically at this stage, and as we've gone into, we've built our ecosystem. We have our modules, every type of vegetable has its own container, and you are going to put them together and make salads, right? That's basically our strategy. What we found is that you do a lot of good science when you slow down. You don't do the slash and burn. You slow down and start thinking about what's going on. This is a cartoon that was on the wall in Bappar's office. You can't see the very bottom of it, but it says, putting a box around it, I'm afraid, does not make it a unified theory, right? So before we had bunches of pieces and we sort of put a box around them, we said, we have something. Now we really, hopefully, can do something. I'll give you an example, which is that, our conceptual DFT code, because we were thinking very systematically computes reactivity indicators to arbitrary order. So if you would like to know, the 18th derivative of the density with respect to the number of electrons, we will compute that for you, right? I don't recommend it again, but I mean, this is definitely publishable in Journal of Molecular Modeling if anyone wants to do it, right? So we had a universal computational framework for conceptual DFT. We realized some very weird things like that, problems with like the exponential model for the energies and things like this, because we started scrutinizing things. This sort of going to arbitrary order response theories. We ended up coming up with a new universal framework for wave function methods, because once you start implementing wave function methods, you want to make it as easy as possible. So we came up with a new framework. And we started thinking about new ways of making wave functions that were size consistent and computationally affordable. Like these things sort of just fell out of thinking systematically and building carefully rather than just trying to hit the objective as fast as possible, right? Right. So I'm going to go through the modules here. I think I still have a little bit of time. So IO data, I told you a little bit about it. It's something about converting and reading various file formats. You can go to the next slide. And we'll see how this works. So all you do is you put in your file, you load it, right? You'll notice there's load one. If you wanted to do like a intrinsic reaction coordinate, you use load many. It's that simple. You can load many on a directory and you'll get a sequence of structures. Probably space. Yes. Oh, back. So here we loaded a file and then we're just going to print out a bunch of properties, right? So we print out the number of atoms, the atomic coordinates, the atomic numbers, molecular orbitals, molecular energies, all of that sort of thing. You can get it out of any file that you can read, basically. And then the next thing is, and this is really the one that Raimundo was most involved in, was grid. And you'll get a sense. I added some extra data on grid here to give you an idea of how hard Raimundo was working. So a lot of people can do numerical integration in their DFT codes. It's somewhat less common to be able to do interpolation and differentiation on your DFT grids, but sometimes that's important, right? So we definitely coded that up. And the main purpose of this was DFT, but we also have periodic boundary conditions, and we can and do use it there. And here you'll see we're just going to build a grid. This is a Gauss-Chebyshev grid. Then if you hit space, probably space. Yeah, just space. Yeah, okay, yeah. So then we're going to build a radial grid. This tells you the first point of the grid. And this is, most of you know, there's some sort of scale parameter. So this is the scale parameter, they call it R0. Then we're going to build a molecular grid. We have atomic numbers, atomic coordinates. We have something that tells you how fine we want our grid. And this is cut, but this is the Becker transform. So this would tell you how to transform the grid. And then finally, we'll print out the number of points and weights, right? So there are 40,000 points in this grid, roughly, right? Now, yeah. So yeah, one back. So G-basis is the one that we use for everything dealing with Gaussians, right? So all the integrals, all the evaluating functions with Gaussians, things like this. And this is entirely in Python. It's not intended to be the fastest code in the world, right? But it can do so much stuff, right? And it's not stupid slow. In fact, for evaluating the density and the gradients of density, it's faster than the old C++ code, right? So it's not stupidly slow, right? And for most integrals, it has the same performance as PySCF because we stole some stuff from PySCF. And for some integrals, it can do them and PySCF can't. So do you care if it's slow, right? Now space. So the thing I like about this is just emphasizing how intuitive something is. And there's an I here that shouldn't be here, but this is the definition of the density matrix, the way we learned it in class, right? So what would you just think if you were just trying to code, you would say, well, I need to multiply together my MO coefficients with my molecular occupations, and then the transpose of the molecular orbital coefficients. That is the expression you want, right? So, well, that works, right? You hit space. So then we bring in our basis set. You have to do this to evaluate something on a grid. Like, it doesn't even use the grid, it just uses the arrays. Then we'll evaluate the density here. And here, I think I just print the shape of the density space, probably. Yeah, no, it's okay, yeah. And then, well, you can read it. For the shape of the density, and we do integrals and just make sure that the water molecule, which is what we're using in this example, has 10 electrons, right? So very good precision with this grid. This is 40,000 point grid, right? This is the sorts of things that we were playing with Raimundo. So for instance, everyone in grids uses what they call Lebedev grids, right? There's another side of grids called spherical T-designs. And in some ways, they're similar to Lebedev grids, but the one thing about them is that they exist to much higher orders. If I want, you tell me to give me you a Lebedev grid with a certain number of points, I may not be able to do it because they only exist for certain very special numbers of points. Spherical T-designs work for any odd number of points, right? So that can be handy. We were disappointed that, well, up to about 200, 300 points, they work the same quality. For lots and lots of points, the spherical design is like one order of magnitude worse than the Lebedev grids. Still okay. I mean, for the flexibility you win, it's so useful sometimes. We use this actually a lot in our quantum theory of atoms and molecules code, where we need better control over our angular integrations. And then this batch of spaghetti, right, is what we did for our radial grid. So when you do molecular grids, you need an angular grid and a radial grid. And poor Raimundo implemented all of these radial grids, right? Because in the end, you want to choose the best one, right? And then tested it. This is for the kinetic energy density, but you test it for the exchange energy, the correlation energy, the density, integrating the exchange correlation potential, integrating the Weizsäcker kinetic energy, differentiating for the Weizsäcker kinetic energy, like all of these different things. You have to assess all of them and see what method works the best. Now, I can't tell you what method works the best because I'm colorblind and I have no idea what that is. But I promise you there is one, and the same one shows up over and over again. So now it turns out that all of these were a waste of time, but we didn't know that when we did it, right? So. Okay, so this is our partitioning code. We have two types of things in here. We have information theoretic atoms and molecules, or Hirschfeld I, or additive variational Hirschfeld, or scaled Hirschfeld, or iterative stockholder analysis. All of these live here. And then this is technically also information theoretic, but it works in a totally different way. And I'll show you this. So all we have to do here is we put out our atomic numbers and where they are. We build a guess for the density from that. And then this actually just runs and converges, and you can hit space. And at the end of this, you can print out your atomic charges and your multiple moments for water, for example. This would be more riveting if I was running it in real time, but nonetheless, it proves the point that I was willing to run it in real time, right? Next. So AtomDB is something, it's just very much fresh off the presses. This is atomic molecular project. So it has a extended database of the periodic table. It has not only atoms, but all the charged atoms, all the excited states of atoms. And we have a good bit of different types of data for charge and multiplicity states. So, and we have experimental data from the National Institutes of Standards and Technology in the US, but we also have like essentially extremely accurate Hartree-Fock functions, extremely accurate sort of Gaussian basis at wave functions, at the Hartree-Fock style. And then slowly but surely, I think we're through Argonne at this stage. We also have sort of benchmark accuracy, it's not full CI, but full CI quality data with a quadruple zeta diffuse covalence basis set. So if you want to know what really good atomic densities look like, we have them inside here. So here's an easy example. We're going to load this up from NIST. We're just loading up the carbon atom, and then we can hit space. And then you just print out certain things, right? It has a lot of other data than this. It has ionization potential, it has the hardness, it has the chemical potential, it has the covalent radius, it has the van der Waals radius, it has the C6 coefficient. All of this stuff is just different field. All of it's stored if we could find reliable data, right? So this is a very tedious task that an undergrad wasted a summer doing. Right? You also, now I'm going to do, this is Slater. So these are Hartree-Fock calculations done with very large Slater basis sets that were designed to get the cusp right, which is useful sometimes. And then we will just, print out, how many spin orbitals they have, what are the occupations, what are the orbital energies, things like this. Right. Okay. And now you can build promolecules. So I put 2 beryllium atoms at, I think it's space, at 2 positions, right? Then I just make a promolecular density. And then, I could print, the mass, I could print the energy. It just adds things up. It's smart. If you tell it an extensive property, it just adds them up. If you tell it an intensive property, like the ionization potential, then you have to tell it what type of average you want to take. So you can take an arithmetic mean, a geometric mean, whatever you believe is the right way to average ionization potential, say, right? And then here's the plot of the promolecular densities, right? Now, one neat thing about this, not that it's interesting for the beryllium dimer, but this is the example I had on hand. If you said you wanted to do this for like lithium hydride, you can assign charges and multiplicities to your atoms, and it will automatically adjust your densities to get the right charges and multiplicities, right? So it'll build an atomic density with the charge and multiplicity you specify, even a fractional charge or a fractional multiplicity. It'll build it in the right way, and then you get a better promolecular density. So this is our CI code. Right? So this does anything that's configuration interaction. And I alluded to the fact we had a unifying framework for wave function theory. We call it the flexible ansatz for n-electron configuration interaction. It's basically a way of parameterizing configuration. If you think about what coupled cluster is, it's just configuration interaction, but your CI coefficients are now some fancy function. And so we decided to exploit that, and that's the way we code things. I'll show you an example here. So here is example of building a very complicated configuration interaction wave function, right? So we're going to start by building a Hamiltonian. This is an empty wave function. Then we'll add in seniorities. So seniorities means I'm going to choose all the determinants that have all the electrons paired, only 2 unpaired electrons or only 4 unpaired electrons. And then I'm going to, on top of that, add all the 4-fold excitations. And then something that I did with James, wherever James is, back when James was a PhD student, we're going to go through what's called the Grebo-Napeck CI algorithm. And we're going to add any determinants that it thinks are important that we haven't already hit, right? And then we'll just find the 4 lowest eigenstates. And then we say, that's still not good enough, and we'll add Epstein-Nesbitt perturbation theory to estimate the contribution of the rest of the determinants, right? So you can do some very fancy things. And so when I say we have essentially perfect accuracy for our atomic densities, it's because we have the ability to do this sort of stuff, to choose determinants very, very carefully to get good answers in space. And then this is a parameterized CI calculation, or a fancy calculation. This is pair coupled cluster doubles, which is sort of becoming standard. It's something that was actually, it was going on when Raimundo was in the group, but it wasn't really what Raimundo was working on. And then we decided to add singles on top of it. And we just define this object using the Hamiltonian. We guess with zeros. We also have to guess the energy. We just give it the Hartree-Fock energy. It's a guess for the energy. It'll be okay. And then we just literally just dot optimize this, and we'll get out the results at the end, right? So getting calculations done becomes relatively easy with this sort of thing. And so you can build, and really, so I had, I taught a programming course last February. There were people in there who had really never programmed before. And some of them wrote new types of wave functions using this code. And some of them wrote new types of ways of selecting Slater determinants using the other code, right? It becomes an exercise that, was a introduction to programming exercise. So it's really quite easy to do. So ChemTools is all the post-processing stuff. ChemTools does not run on my Windows computer, so I could not generate a ChemTools figure for you last night. But I have a ChemTools figure that I took from a paper, and I have the script that was used to generate it. So I'll give you an idea of how easy it is to do something. So if you give me a space bar. So this figure shows up in a paper. This is 2,6-dichloropyridine. I'm sure I was talking about it when I was here 20 years ago. This is one of my favorite molecules, has been since I was a PhD student. We give you the molecular structure, the electrostatic potential, Fukui plus, Fukui minus, and dual descriptor, right? And well, we're going to start by computing the density, because this is on the isosurface of the density. So we read in the neutral molecule, and we compute the density. Then we just generate a Q for the electrostatic potential. We compute the ESP on the Q points. It's that easy to compute your ESP. Just dot compute ESP. Then we need to load up our Fukui functions, and then we just generate a cube here, and we just take this tool, that linear tool knows how to compute Fukui plus and Fukui minus. And so you just do tool dot this, and now you compute that on the grid. And clearly the dual descriptor doesn't belong to the linear model of DFT. You have to assume that energy is differentiable to get the dual descriptor. So now you need the quadratic model, but you do the same thing. And then tool dot dual descriptor, and you get the dual descriptor. And then you just pass it to your favorite thing. You have 5 cube files, and outputs your figure, right? So it gives you an idea of how easy it can be to do things like this with ChemTools. Okay, so the last thing I'll talk about is QCEDU. I'm not going to try, I would normally do like a live demo, but we're running out of time and it's going to be too complicated. But I'd invite you to go to the site. I'd invite you to go to it's very easy to remember. It's, qchem.qcedu.org, which is my quantum chemistry site. And you'll find that there's undergraduate exercises there that you open them up, you write a computer program to do something, and the computer program gets automatically checked. Or you get a set of multiple choice questions, and you record them, and they get automatically graded, right? So I managed to make it so that I have less grading to do, which is useful. But you can do much more interesting things than you used to be able to do in your quantum chemistry courses. So we, I have my students in, by 5 weeks, 8 weeks into my class, like they're basically doing numerical proofs of the Peierls distortion and understanding why it happens faster when you have even numbers of sites and odd numbers of sites and things like this. Right? So you can do real things with this. And we do, this definitely elevated the level of problems people in my course do. It also helped because now you don't have to actually do integrals and derivatives anymore. The computer does it for you. Okay, so I want to just talk about my summary slide, which is that I really believe in sustainable ecosystems. And these are my 3 my three main things. The first one is not to slash and burn, like resist this temptation to just hack something and make it work, right? Which is not to say never do it, right? It has a time and a place, right? I say sometimes you have to cut down on a tree to test the soil, right? There's no reason to build a gigantic software package for an idea you're not sure is going to work, right? But once you're sure something is going to work, take the time to do it right, right? So this is the biggest mistake I made early in my career is I invested gigantic amounts of time and effort before I even convinced myself an idea was going to work because I was so bloody confident in myself, right? I always tell my group, like, if I tell you something and it sounds like it is easy to do, it should be easy to do, right? So if I tell you, oh, I believe it should be easy to use your particle hole RPA equation to do time-dependent DFT and to do the orbital Hessian, because I know the mathematical structure is the same. It should be easy to do those things, right? And so make sure your code does that. And that means you're constantly refactoring your code. You're constantly rewriting your code to make it easier to do things that you know should be easy to do. And the last thing, and maybe one of the most important ones, is you have to work with nice people because it takes a team to have an ecosystem. Like an ecosystem is only as strong as its weakest link. And if people don't care about each other and what they're doing. So I know, and this is looping back when I was here in probably was 2018. Raimundo started with me in February 2019. It's probably summer 2018, something like this. And I knew that Raimundo might be interested. And I was talking to several people. It was just like, you know, I have this project. Raimundo seems like he would be a good fit for it. But I remember just like, is he nice? And everyone looked at me like it was crazy that anyone could think that Raimundo was anything other than nice. Like, and it's true. One of the nicest guys you could ever hope to be, right? And when you're starting something new, like Horton 3, it doesn't work unless the person that everyone is talking to is patient and nice and willing to admit when they're wrong and willing to very, 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 very gently tell other people wrong, right? And that was Raimundo. And next slide. So this was the group at that point. Here's Raimundo. This was actually taken in January of 2020. It was right before the pandemic. So here's Raimundo. Zhao was also from Mexico, right? Yep, right. So so there's in fact, this is the Spanish-speaking component. We have Raimundo from Mexico, Gabby from Cuba, Mara from Spain, and Zhao from Mexico. Right? And with that, I'm finished. I'll be answering any questions.
Preguntas. Tu nombre, por favor.
Oscar? Do you have any plans on making a working code with ASE
So
to take some of their tools and
so we use ASE certainly, right? Like I use ASE and RDKit a lot, right? But we interface with them at the level of what I call Horton, which is at the level when we're writing scripts or Jupyter notebooks or something like this for a workflow, we use them as they are rather than, so we have already, it's painful just trying to deal with SciPy and NumPy, which are super standard, right? But they're constantly changing their API or some new feature, old feature becomes deprecated, some new feature emerges, and you're constantly having to update. Less of that we do, the better. We prefer having it in our wrappers, right? So we haven't found the need to integrate deeply with them instead. We use ASE a lot because we made a strategic decision when we were doing IO data to not interface with anything except for, what do I say, public file formats. If we need to parse a Gaussian log file, we're using ASE, right? Because we don't want to support a Gaussian log file because that means every frickin' sub-release of Gaussian, we may have to update our code, right? And so we chose, with Gaussian, we support an FJEC, right? Which is already enough of a pain because they've changed it once, right? So we use them, but we haven't integrated with them. We use a lot of things, like we use PySCF a lot, we use MoPro a lot, we use Cyport a lot, we use Gaussian a good bit, right? And that's one thing, IO Data just makes it easy. We use what we need from them, and then we go on and do whatever else we need to do.
All right, thank you.
¿Alguien más? Alberto.
Do you have some of your parts, especially I'm thinking about the grid work. That is very numerically intensive, highly intensive. And well, actually, from the work of Jorge and his group, including Raimundo's work, if you don't work, if you don't program that in parallel, it's painful. The question is, some of these modules, especially the integration module, are parallelized, for instance, running on GPUs?
So some of them are. So the grid specifically, it is what I would say, and it's very typical for what we do. It's parallelized at the level that the libraries we use are parallelized. In the end, everything we have to do with grid is basically linear algebra. There's some building of spherical harmonics, which we actually put a lot of effort into doing that efficiently because that was slow. But other than that, it's basically all numerical linear algebra. So our default under the hood is NumPy. And if you are working on an HPC system, they should have a NumPy that they compiled in a hardware-specific threaded way. And for most of what we do, that works well, because usually you need to do more than one integral at a time. And we already have some issues with memory handling with grids there. So we've already dealt with that, okay. If you really want to do that with GPUs, and we've done it, but it isn't the default, instead of using NumPy, you use PyTorch. And then PyTorch, with the same command as NumPy, will do all of that, and PyTorch has a GPU implementation. And so we end up leveraging those things that were written by people much smarter than us. That's, linear algebra for a CPU architecture and a GPU architecture. Where we had to do it was when we did the Gaussian handling, right? So when we have GBasis and we have QGbasis, which is the CUDA version of GBasis. And there, for like evaluating densities, electrostatic potentials, gradients of densities, all of those sorts of things on a grid. And some numerical integration there too. Some numerical integration is also done in QGbasis, but pretty much it does things usually on a cube. And there, the performance gain was big, right? I mean, 2 orders of magnitude. But it can't do everything, right? So for instance, GBasis will compute arbitrary order derivatives of the density matrix, and all of these things. So for instance, like James uses that because he likes the Ehrenfest force, and we can differentiate as many times as you might want, right? In our QGbasis, we only hard-coded it because we had to hard-code it to make it efficient up to, I think, d orbitals and second derivatives, right? It just wasn't worth the time. And also at a certain point, the way you've coded it very efficiently would have to change, right? You would, I think it's either F or G orbitals. At that point, if we had supported it, we would actually have to change the way we loaded data into the GPU.
¿Alguien más? ¿Someone else? No? Alberto? No, Joel. Sorry.
Okay, yes. Well, I just would like to hear your opinion about this incursion of these big companies in the electronic structure field. I mean, yesterday there was a webinar of Microsoft talking about accelerating DFT 2,000 times or something like that. I think in our community we are almost software free, and we are used to use software, free software. But I was really curious that companies like Microsoft now is turning their interest into these kind of things. I don't know how, what do you think about that?
Okay, so this is a complicated question. I'll explain why. So I am 100% committed to not just free and open source software, but free and open source and usable, which means it should be documented, it should be structured, there should be a manual, there should be examples. If you ask a question, someone should eventually answer you, right? I believe that's the right way to do science, okay? But I'm also thinking more about doing science than generating vast numbers of numbers, right? There is also a place where it's less about creating ideas, generating new ideas, and more about, I have a database of 20 million compounds, and I need B3 lip energy for all of them, right? Okay, so that's one reason it's complicated. The other reason it's complicated is one of the main people doing this at Microsoft is a guy named Matt Chan, who was the driver behind Horton 2. So I'm not going to say it's my fault, but I mean, he visits me once or twice a year, right? And I think there's really a niche for what they're doing, which is, not all of us have the expertise to program something. Not all of us have the expertise to install a piece of research software, certainly not, and compile it in the way that's optimized for our hardware. Not all of us have the expertise to write a workflow that will, script your calculations, and when it fails due to SCF, tweak the input options in a way that might make it converge, right? And so what Microsoft has done is they put together a team of people, and they've said, well, we're going to provide the hardware. You don't have to install it. We provide the software. We work hard to make sure this software, and they do sit down with these companies that have software and work hard to make that software faster for their computer, right? Which is one reason that it goes faster, right? And then if your job is to generate numbers, right, and that's the task you have at hand, then, maybe you should be doing, I forget, it's probably Fernando Cortez I was talking to. And I said that when we looked at, in Canada, so we have Gaussian licenses for our supercomputers, our shared supercomputers. When they looked at the amount of money they pay to maintain these supercomputers, including the human staff, right? It would be more efficient for the Canadian government to pay Microsoft, right? Because they have economy of scale, right? I mean, they have more people, they have more computers, they're better set up. Probably the average person working at Microsoft in DevOps is better than the average person working at the Canadian Computer Center in DevOps. They're certainly getting paid 2 or 3 times as much, so hopefully they're better, right? And so for economy of scale, right? But I should emphasize, I mean, I decided relatively early in my career that I was not going to try to pursue bleeding edge performance. Like, I was looking at testing ideas, and this is designed to test ideas, right? I want it to be fast enough to be useful so that I can test the ideas. I want to be able to, but I sort of believe if the ideas are really good, then someone will make it work on something else. But, you know, we do end up making it fast. I mean, so the Kuji basis came because, I have a joint student co-supervised with Fernand Sederzada, and this student is looking at trying basically computational drug design with machine learning, and has, you know, libraries with 100,000 molecules. And then he wants to be able to put the electrostatic potential on the van der Waals surface of 100,000 molecules, or the Fukui function on the van der Waals surface of 100,000 molecules. And, you know, we didn't try to build the fastest code. We just tried to build a code that was fast enough to do that task, right?
Okay. Well, before to give the microphone to Professor Alberto Vela, I want to know if there are comments from YouTube people. No? Okay, the last one.
I don't remember.
Okay, so, ¿alguien más tiene algún comentario? ¿No?
You don't have adaptive grids in your grid module, right?
So by adaptive, you mean pruned, or by adaptive, you mean subdividing until you get a certain accuracy? We have scripted adaptive grids. So it isn't part of grid module. We've done it as a wrapper around it. For cubes, it's easy, right? What I really want with adaptive grids is a project that actually it started also with Raimundo. There was a lot of things that started with Raimundo, and the pandemic kind of got in the way. Yeah. Yeah. So yeah, we can talk about that. So the main thing is I want to, with adaptive grids, I want to make sure that when so I'm most interested in molecular grids. With cubic grids, it's easy, right? We have a rough adaptive grid that we use for quantum theory of atoms and molecules. But honestly, it wasn't, so I was so happy about this adaptive grid. It was beautiful. It's a beautiful mathematical idea. It could not compete with Becker-Lebedev grids, right? The price you pay by making something that was adaptive in that case was more than what we gained, right? So what I'm trying, and this is the thing I started with Raimundo, is adaptive grids, but they need to be nested radial points and nested angular points. I don't want to be, when I refine it, have to recompute my function at points. I want to read the points from the small grid of the next biggest grid, reuse those points in the next biggest grid. The catch is, when you want to do this on a sphere, there's only the cleverest way I can figure it out. So I'm not going to say there's no better way. If you want to reuse all of your earlier points in your next points, every time you add points in the angular grid, they increase by a factor of 4. So it's not doubling, it's increasing by a factor of 4, which makes sense. It's 2 dimensions, right? Which means that you end up making big jumps. You know, you go from 100 and some rate angular points, which is fine. And you might think, oh, maybe I need 300. Well, you can't get 300. You get 768, right? And so once again, I'm a little bit worried. It may be that the adaptivity, you end up losing it because you end up having to use so much extra points just to keep the adaptivity. So we have a strategy for it, hasn't been implemented. So I'd be happy to talk to you about it.
Okay.
Maybe before
Well-
something.
Well, before Edgar read your certificate,
Mhm.
I want to give you a present in
Okay,
behalf
no.
of the chemistry department.
No,
Thank you so
very
much for this.
Okay,
Thanks.
no, thank you. Right.
Thank you very much for your presentation, Professor Paul Ayers. Now your certificate is in the screen. El Departamento de Química de la UAM Iztapalapa otorga la presente constancia a Professor Paul Ayers por impartir dentro del ciclo de seminarios del Departamento de Química del trimestre 24P la conferencia Building an Ecosystem for Research and Education in Theoretical Chemistry. El día 3 de octubre de 2024 firman el doctor Jorge Garza Holguín, jefe del Departamento de Química, y el doctor Edgar Carrera Crespo, coordinador de seminarios. Thank you very much.
Thank you.
Agradecemos a los que nos acompañaron. Sí, agradecemos a los que nos acompañaron de manera presencial en el Salón de Seminarios Serie 206 y a los que siguieron la transmisión por el enlace de YouTube. Buenas tardes, somos Guamis Tapalapa, somos Departamento de Química, somos Panteras Negras. Buenas tardes.
Thank you very much.
Thank you. Continue that to work that hard. But now you see more of why I said.